Hello everybody and welcome back to our Artificial Intelligence course for biotechnology. So far we have learned about different classification models like k-nearest neighbor and logistical regression, and we have also learned about regression models like linear regression. Then we extended the concept on regression models by using regularization techniques, for example L1 regularization to do internal feature selection and L2 regularization to account for correlated features. And then we also looked at different ways how we can measure the performance of such models and how we can do cross-validation to get empirical estimates. In this lecture now, we will look at a different class of model called support vector machines. In this lecture, we will now motivate what is a support vector machines and why are the support vector machines so powerful. And therefore, we will first look at a small motivation. Then we will introduce you to the hard margin SVM and the soft margin SVM. And then we will extend the concepts by using kernels. So let's start with a small motivation. So let's assume we are given two features, x1 and x2, and we have different data points which are visualized here. So in green, you can see data points that belong to class 1, and in black, you can see data points that belong to class 0. So we would like to predict new samples now, or the class label of new samples, by using a decision function that separates these two classes. So if the data is linearly separable, there exists a line that separates these two classes, and that can be used then to make predictions. So for example, here you can see a linear line, and this, as you might know from the linear regression lecture, has the following form: W transposed times X for sample I, so the features for sample I, plus B, where B is the bias. So W transposed is nothing else than beta transposed, and X I is the sample, all the features for sample I. If this is equals to 0, then we know that we are exactly on the line, which means then if the value is less than 0, then we are here in this space here, then we have classified data points that belong to class 0, and if the function has values that are greater than 0, then we are in class 1. So we can use this decision function to do classification. This decision function is also very often called hyperplane. So let's look at some notations again. I already introduced you to the W. W is nothing else than a weight vector. So in support vector machines, they don't call it vector, they call it W, and they say the W is a weight vector. So it has a specific, each feature has a specific weight. And actually it's nothing else than what we have learned in linear regression. And B is called the bias or the intercept that you also still know from linear regression, where B, beta 0 was equals to B. Other thing which we have to name here, or that we have to introduce you, is the inner product. So you know this dot product W transpose times Xi, and in support vector machines we very often use the inner product here, that we write this angle brackets here, the special angle brackets, then we write W comma Xi, which is nothing else actually than here the dot product between the vector W and the vector X. And this can be also expressed as the following. So the distance or the length of vector W times the length of the feature vector times the cosine of an angle. So this can be also interpreted in a geometrical way. So how can we do now predictions? I already told you that if we are exactly 0, then we are on this hyperplane or on this decision function. If we are less than 0, we are in this half space here, so we could classify points that belong to class 0, and if we are greater, we are in this half space, so we can classify points that belong to class 1. This can be mathematically expressed using the sine function. So the sine function here is 0 if z is 0, it's plus 1 if z is greater than 0, and it's minus 1 if z is less than 0. So we can then say our function xi, so for our data point, for our sample xi, gets classified using the sine of this linear line here, and if it's less than 0, we classify the point to be in class -1, otherwise in class +1. The problem now is, if we look at this plot here, is that we don't know how to find this hyperplane. So the problem is, how do we know that this hyperplane or this decision function is the correct one? Why is it not this one? Or why is it not this one or this one? So the problem is that if both classes are fully linear separable, then there are infinitely many decision functions. So there is a huge amount of these decision functions, and now we have to select the best one. And how do we do this? And there we introduce you to the so-called hard margin SVM. The hard margin SVM was more or less developed by Vapnik and his colleagues in 1974. And the idea was that we not only try to find such a line here, we try to find a line, a decision function, that has a margin. So there's a margin around this decision function, and we like to find a line that maximizes the margin between any training point and the hyperplane. So here we have the training points, and we like to now find the margin or in such a way that the distance of the margin is maximal, and that the separation between the training points is such maximal. So if we look at this example here the blue line is again our decision function, the dashed green line is our margin. Then we have here this W vector, which is orthogonal on the decision function. And then we like to maximize the margin here. So the margin is 2 divided by W squared, and we like to maximize the margin. The circles you see around these dots here are called support vectors. So the support vectors are those points that lie exactly on the border of the margin. And the interesting thing is that we can do predictions. We only have to know the support vectors. We don't have to know anything about the other points anymore after we found the support vectors. So the goal is now to find a decision function in such a way that the margin around the decision function is maximized between the training points and the hyperplane. And then we found these points that describe the margin more or less. So with these 3 data points, we can exactly describe the margin and the decision function, and then we can do predictions, and then we can say everything which is here on the left half space is classified to belong to class -1. Everything else is classified to be in class +1. So to summarize this, we have training data, but now the labels are -1 and 1. These are the 2 classes we have. And then we have the following constraint optimization problem. We like to minimize, with respect to W and beta, the following formula. So 1/2 times W squared, so the L2 norm squared, subject to the following formula. So why do we first of all like to minimize this stuff here? That's because our goal was to maximize the margin. And the margin is maximized in such a way that all training instances of the same class are either on or outside of the margin. So to maximize the margin, we have to minimize W, because if we remember, the margin was 2 divided by the L2 norm of W. So if this gets small, the margin gets maximal. That's getting then larger. So we have to find the minimal W. So why do we need the following constraint here? We need the following constraint to be greater or equal to 1, because this constraint ensures that all the training points of the same class are on the same side of the hyperplane. If we don't have this constraint here, then we can't ensure that all the training points that belong to the same class are on the same side of the hyperplane. So don't be worried if you don't know too much about solving optimization problems so far. In this lecture, I only like to give you a very high-level overview or summary on how to solve this optimization problem under inequality constraints. If you like to read more about these concepts or review some of your knowledge that you learned in your first semesters in mathematics, we suggest you the following readings. So there is a very great book, a very recent book, which is called Mathematics for Machine Learning, which is freely available under this URL. There in chapter 7 and in chapter 12, you can read about, first of all, continuous optimization and then how it is done for the support vector machines. And there is also a very important book, which is called Elements of Statistical Learning, which is written by some of the best statisticians in the world, so Hastie and Tibshirani and Friedman. And there in chapter 4.5.2 and chapter 12.2 to 12.3, you can find also details about optimization problems and how to solve it for these SVMs. I only like to give you now a very high-level overview of what a constraint optimization problem is and how we can solve it. That's important because we need some of these things later in this lecture to understand why support vector machines are so powerful. So let's first of all illustrate or give you an intuition about a constraint optimization problem. Let's assume we have here this optimization landscape. So we have here a landscape, and usually in a normal optimization problem, we would like to find the minimum of this landscape. And the minimum is here illustrated as this red dot. So that's a normal unconstrained optimization problem. However, we also could say we would not like to find the minimum of this function. We like to find the minimum of this function that is within a specific area. Let's say here this blue box, which you can see here, that's an area between a -2 and -1 on the x-axis and 1 and 2 on the y-axis. And we would like to find the minimum of this optimization problem in such a way that it's within this area. And then this is illustrated here now with this star, this blue star. That's the minimum under this constraint. So we more or less restrict our optimization problem to a specific area where we like to find the minimum. And this can be used in support vector machines, because in support vector machines, here we say that our constraint is the following, which ensures that all the examples that belong to one class are on the right side of the hyperplane. So how to solve now such an optimization problem? And here I like to give you only a very high-level overview. This can be done with so-called Lagrangian. The Lagrangian or Lagrange, I don't know how to pronounce it correctly, is defined then as the following. So we can write this constraint optimization problem in such a way. So L is here not the loss, it's the Lagrangian, is 1/2 of the L2 norm squared. So this part here minus the sum over all training instances of this part here. And then we introduce here an additional variable that's called the Lagrange multiplier. So the Lagrange multiplier has to be always equal or greater than 0. And then we have here a so-called Lagrangian. And now I introduce you to something that you very often read when you deal with support vector machines, the so-called primal variables and dual variables. So duality is the thing when you try to convert an optimization problem in one set of variables. So here we have W and beta. These are the so-called primal variables. If we like to convert the optimization problem that's based on this set of variables, our primal variables, into another optimization problem in a different set of variables, that's our alpha I, that's called the dual variables. So what we try to do now is we try to convert this optimization problem here by finding the minimal W and minimal beta into another optimization problem that is then dependent on alpha. And here we have to say that the Lagrangian is then minimized with respect to W and beta, and it's maximized with respect to the dual variables alpha I. If you like to read more about this, you can take a basic mathematics book to read about a constraint optimization and that will be described in more detail. So let's look at this reformulation of the Lagrangian. So we have here now the formula from before, and first of all we simplify it. So we take apart this sum here, so that's then nothing else than here again the L2, the squared L2 norm times 1/2, and then we have here the sum over all samples from this expression minus this expression plus here the sum over all alpha i's for all the samples. So we just took apart here this summation here. And then we said here that the Lagrangian is minimized with respect to the primal variables w and beta. From before we know, from the lectures before, we know that finding the minimum of a function is taking the derivative and setting it to 0. So the partial derivatives of the Lagrangian are 0 at optimality, which means we first take the partial derivative with respect to beta. Because, as I said before, we have to minimize with respect to w and b. So the first thing is, here we take the partial derivative with respect to b and set it to 0. So let's do this. We take the partial derivative here with respect to b, which means this part disappears, there's no b inside. This part disappears, there's no b inside. This part has a b, so if we take the derivative of this minus the sum of I to n of alpha I yi is left. That's the derivative here, and this part disappears again because there is no b inside. So we can then solve this equation. So it's then minus the sum of I to n of this expression is equals to 0. That's what we now found out. So this part is 0. Then we take the partial derivative with respect to w, which should be also set to 0. So we first take here the partial derivative. So here we take the partial derivative, it's then w minus here the sum of I to n of alpha I yi xi. This part disappears and this part disappears because there's no w inside. So then we can solve for w. So w is then equals to the sum of I to n of alpha I yi xi. And these alpha i's are called our support vectors. So in the moment if alpha I is greater than 0, then we found a support vector. All the other points are set to 0. So we like to find those data points that are now on the margin of our on the margin. So we took now the partial derivatives and we found these expressions here. And what we can do now is we can create the dual formulation of this problem. So here we have again the Lagrange, and now we substitute here the w's with this expression here, which we computed on the slide before, and with this expression here, which we also computed on the slide before. So let's rewrite this. So here this is nothing else than w transpose times w minus this expression minus, so I put here the b in front because it's independent of I, so b times this part here plus alpha, the sum over all alphas for the samples. So here we can see this part is equals to 0. So this part disappears. W we replace with this, and then we have w transpose, which we can replace with this. So we get then in the end minus 1/2 of the sum from I to n, of the sum from j to n, of this expression here. That's just that we replaced w with this expression and this disappeared. And the nice thing now is that this reformulation now is completely independent of w. So the optimization problem here accesses our training data only in terms of inner products. No w anymore, no b anymore. And that's very convenient because with this we can now train our support vector machine. So to summarize this, the training data is the same as before, just that our labels are -1 and 1. The training is now maximizing the Lagrangian with respect to alpha using this formula here. That's our optimization problem that we like to solve with subject to alpha I greater or equal to 0, and that this sum is 0. And then we can also do predictions independently of W by only knowing the support vectors here, alpha I. So that's then nothing else than this expression. So you could see that we got rid of W by reformulating the optimization problem using Lagrangians. So if we now look back at this example here, then we have seen that we can now found this decision function that maximizes the margin to our training points. However, do you think there might be a problem? One problem is that this formulation that we just derived only works if both classes are linearly separable. We can't find a solution if the data is not fully linear separable. And in reality, you won't find problems that are so nicely separable, or they might be very trivial to solve, then we don't need a classification algorithm. So in reality, we have something like this. And how can we solve, or how can we find here a decision function that separates these two classes? And the idea behind this is that we allow misclassifications of some of the training points. And this was published in 1995 by Cortes and Wapnick. And the results looks in the following. So we have here also a decision function again, and here a margin around it. And we have now an additional penalty parameter C. And C adjusts now the degree of allowed misclassifications. So how can we do this? In the soft margin SVM, as it is called, we try to extend the classification problem in such a way that training points that are now that training points are now allowed to lie within the margin or on the wrong half space. So that's the errors we make. And how can we achieve this? By introducing here this extra term. So we add here a new variable that's a Xi. So Xi is a so-called slack variable plus C and the sum over all the slack variables for all the samples. And here we also extend the constraint by minus the minus Xi, and Xi has to be larger or equal, greater or equal to 0. So what does this mean? So the slack variable Xi measures the degree of misclassification of each of the training examples. So here we measure how many errors are we allowed to make. And the parameter C, that's our penalty parameter. This penalty parameter now determines the trade-off between maximizing the margin, so that this gets larger, and minimizing the training error. So that's the training error. So if C gets larger, then the training errors are more important, that we don't do too many errors in the training. If C gets small, this term gets less important, so it's more important to maximize the margin. So let's look at this optimization problem a little bit more closely. So this was the optimization problem that we like to look more. So now we take again here this constraint. So we take this constraint and we can rewrite this constraint by substituting this stuff by f of xi. So this is nothing else than our linear function that gets the point xi. So yi times f of xi should be greater or equal than y minus xi. We know from before that xi has to be greater or equal to 0. And that means that the constraint here is nothing else than if we solve for xi. So xi is then the maximum of 0 because it's not allowed to get smaller than 0, or 1 minus, so 1 minus this equation here. So we can now express xi as this formula. And why is this important or helpful? Because now we can substitute here this xi with this formula. And then the constraint optimization problem is then converted into an unconstrained optimization problem of the following form. We now can compute the minimum with respect to W here 1/2 times the L2 norms, the squared L2 norm, plus c times the sum of I to n, so for all the samples, and of here, which we have substituted the maximum of 0 or 1 minus y times f of xi. And that thing is called the hinge loss. And this formula might be very familiar what we have seen before. Because when you remember what we have seen, for example, in ridge regression, then we had a loss function in ridge regression. We had a penalty term, which is here very similar. We penalize the weights of our regression, but this time the penalty parameter c is in front of the loss, which means that we like to penalize the loss, so the misclassification of our data points. So this part here can be used to penalize if we did correct or wrong predictions. So what's now the effect of c? So let's look at an example here. If c is large, then we have a small margin and we make few errors. So we have a huge danger of overfitting because we might find a decision boundary that is too narrow. So let's look at the formula again here. If c is large, then we have a small margin because we then penalize wrong predictions much more strongly. Large c favors this term, so it ensures that the margin gets small. This term is not so important than the misclassification, so we make few errors and we have a small margin. The other way around, if we have a small c, then we allow a lot of errors and we are getting a large margin. So that's then the danger of underfitting. So if the c value is too small, we have the danger of underfitting because our margin is too large and we make too many errors. If c is too large, then we make only a few errors on our training data, and our margin is small, which then leads to the danger of overfitting. So what we would like to find is the optimal c value that leads to a model that generalizes well on unseen data. So we like to find a trade-off between maximizing the margin and minimizing the training error. So that's the trade-off that we have to find. So c, again, is a hyperparameter that we have to tune in our model. So far we have now learned about hard margin SVM, and that the hard margin SVM only can be used for completely or fully linear separable problems, and the soft margin SVM is a more general form of the SVM that allows misclassification and such allows to find a trade-off between maximizing the margin and minimizing the training error. In the next few minutes, I would like to introduce you to kernels. And kernels are the thing that make the support vector machines so powerful. So first of all, I would like to explain to you what is a kernel and how we can combine the SVM with the kernels using the kernel trick. And then I introduce you to different types of kernels that are out there. So first, let's motivate this example. Let's look at this following plot. Again, we have two features here, x1 and x2. And we have here data points that belong to class 1 and data points that belong to class 0. If we would now try to find a line that separates these two classes from each other, we won't be able to find a linear function that is able to doing this, because the problem is not linearly separable. It's not possible that we can find a line that separates these two classes from each other, such that all the data points of class 1 are on one side of the line and all the data points from class 0 on the other side. But we can look at it a little bit more closely. Let's imagine the following. Let's try to transform our features, which are in our two-dimensional space, so x1 and x2 are 2 dimensions, into a higher dimensional space, in a, for example, 3-dimensional space. So first we have here some data points, x1 and x2, and we like to transform them with some transformation into a higher dimensional space. For example, that we then get x1 x2, these are our first two dimensions, and the third dimension should be then, for example, x1 squared plus x2 squared. So if we do the following, I will show this to you in Jupyter Notebook, then we have here again this plot that you have seen before. Here some data points that belong to one class and some data points that belong to another class. And when we now transform it into a three-dimensional space, then you see that in a three-dimensional space, these two classes get linearly separable, because now we can find a plane, a hyperplane, that can separate these two classes in a higher dimensional space from each other. So now we can use the concept again of linear functions, or in this case of linear hyperplanes, that separate these two classes from each other. That's very nice. So I have this here also in the slides. We have here this transformation that makes the data linearly separable. And this hyperplane then separates the data. However, there's also a problem associated with it. We have to know how we compute this feature transformation. And we have to explicitly compute it. So if we go back here, then we see here that we have here two features. That's the data we are given. And now we have to find some transformation that transforms our data into a three-dimensional space, or in a higher dimensional space, that the data gets separated. In this easy example, we found this by just trial and error, for example. But we have to really know and explicitly compute it. And the problem is that this is not feasible for infinitely dimensional spaces. So sometimes we are not able to explicitly compute this feature transformation. And that might be a problem. But let's first look at our problem again from before. When we have our support vector machine and we are given our data, then we also can apply some transformations onto our features to map the m-dimensional the feature in the m-dimensional space into an infinitely dimensional space. We can map it into some other space. So we can replace here this inner product between xi and xj by the feature transformation of xi, and the feature transformation of xj. And this can be also then plugged into SVM prediction. So we can now, using this feature transformation, we can now separate nonlinear separable problems by using this feature transformations. And now I come to the kernel trick. So what's a kernel? Let's assume that data points xi in our, which have m features, are mapped into a space that we call H. So we map the data point xi into another space H via some arbitrary mapping function phi. So phi maps this data point into this space. A kernel function now, so k, is defined as the inner product between data points in this space H. So a kernel function k of xi, xj is nothing else than the inner product of this feature transformation of xi, the feature transformation of xj. That's the formal definition. So a kernel is a similarity function between our examples xi and xj. And the similarity function implicitly defines a nonlinear feature map. So what does a kernel do? An optimal kernel assigns to all the training instances a higher similarity value if they belong to the same class, and a smaller similarity value if they belong to different classes. So with this definition now, we can define what we have seen what's the definition of a kernel is. And now let's again motivate a kernel again. So if we go back to the example from before, then we said, okay, we can compute some transformation to a higher dimensional space to make the problem linear separable. However, there exists many high dimensional spaces in which these examples might be linear separable. So for example, this would be now a different high dimensional space where the problem is also separator. So here again, we have to compute explicitly this feature map or this transformation. We have to know this formula that we can compute this third dimension. So now let's look at the so-called polynomial kernel of degree 2. So a polynomial kernel of degree 2 is nothing else than x transposed x squared. So let's assume now that our vector x contains two features, x1 and x2. So we pass here x1 and x2 to this kernel function, and then we replace here x transposed x by this vector, and we compute it. So x transposed x is then nothing else than x1 times x1 transposed plus x2 times x2 transposed. That's the formula that we have learned in the first lecture, where we defined what's the dot product between two vectors, and then it's squared. So with this formula, we can directly compute the result, which then more or less tells me how similar is this sample to this sample. It's nothing else than a similarity measure, what we computed here, because it tells me how distant these two samples are from each other. So the closer these samples are together in this space, the more similar these samples are. That you might remember also from the Euclidean distance. So now we also could look a little bit deeper into this formula and try to also compute here what's written here. So we can then also say this is nothing else than 2 times x1 and so on. So this is equals to this. And then we can rewrite this formula in the following form. This is then nothing else than the square root of 2 times x1 times x2, comma x1 squared, comma x2 squared times the vector transposed. So if we now look at this formula here, then you see that's exactly this formula that we computed here to separate the data. And the nice thing is now that when we compute here this kernel, this formula is much simpler to compute than this formula here. So when we have this kernel, this polynomial kernel of degree 2, we can exactly compute here a result. And this result, which we computed here, implicitly maps the data into a higher dimensional space, which you can see here, which we don't have to compute because we already computed it here without solving it. So this is the feature map actually that this kernel describes. So here we can compute the solution in this lower dimensional space implicitly for this higher dimensional space. And that's called the kernel trick, because now we can replace here this inner product between the feature space with a kernel function. And then we can use kernels for doing predictions. And that's why support vector machines are so powerful, because we can now use different kernels to map our data implicitly into a higher dimensional space to make them linearly separable, and then we can use the support vector machine to classify them. And we even have to know how this space looks like or how many dimensions we need, because it's done implicitly by the kernel function. That sounds a little bit strange and also very difficult to understand. So I recommend you to go over the slides more closely again and think about some of the ideas. So let's look at some common kernels. That's the linear kernel, x transposed x prime. This is nothing else than you know from before. That's a linear kernel, and with this linear kernel we can't separate nonlinear problems. So therefore we need more complex kernels. For example, like here the polynomial kernel, that's the generalization of the example from before. So we have here degree d, so we can also compute polynomial kernels with degree 3 to 10 or whatever. And here we have the so-called Gaussian radial basis function kernel, or short RBF kernel. That's nothing else than a Gaussian, so a normal distribution in a more dimensional space. And the interesting thing about this RBF kernel is that the feature space of the RBF kernel has infinite dimensions. So with this RBF kernel, we can implicitly map our data into an infinitely high dimensional space without even computing it. And that's very powerful because this allows us to more or less separate problems in an infinitely dimensional space and make them linear separable. So the thing is, you can see here this lambda and here D or C. These are all additional hyperparameters which we might have to tune when we train our models. So let's look at some examples. Here I have two classes again, class 1 and class 0. And here, these classes you can see directly in this plot are not linear separable. So when we fit here linear regression, for example, we might get with a specific parameter C the following decision boundary. And there you can see, that doesn't look very good. Now let's take a different kernel. So we map it implicitly into a higher dimensional space with a polynomial kernel of degree 3. Then you can see that we get not a straight line as a decision boundary, but this curve. So we describe our data, or we can separate our data much better now compared to this linear function here. And when we use an RBF kernel, then we map it implicitly into an infinitely dimensional space. And now you can see that we get a much sharper decision boundary that describes our data very well. However, you might also see that the models get more complex the more advanced kernels we use. And also, this means also that the likelihood that we overfit our model increases a lot. And you can see here that the choice of the kernel matters. So usually in practice, we start with a linear kernel to see if we can separate our problem with the most simple kernel. But if this doesn't work very well, we then take different kernels to see if we can map the data implicitly to a higher dimensional space to make them separable or classifiable. And the nice thing about these kernels is, as I said before, they more or less describe nothing else than a similarity measure between our samples. There exists a huge family of different types of kernels, and kernels can be computed on so many different things. For example, there are kernels on structured data. Let's look at this example. We would like to predict whether a specific protein is segregated or not, only based on the sequence we get. So we have here the amino acid sequences of a protein, of secreted proteins and non-secreted proteins. We like to predict if they are secreted or not. And therefore we could, for example, use the so-called spectrum kernel, which is nothing else than that X and X prime are the strings. These are the strings, the individual strings, and S and S prime are the sets of all their substrings. So we take one of the strings and we chop it up into all possible substrings. And what this kernel is doing is then, this function increases by 1 for every pair of matching substrings. So if I find here a substring, and if I find here a substring and they match, they're exactly the same, I increase the counter by 1. So what we get then is a similarity measure between all the different strings in our data set, and it tells me how similar specific strings are to others. And then this spectrum kernel could be used to do classification based on strings. There are other kernels, for example, to compare graphs. Sometimes, or very often, we would like to predict whether a specific molecule is toxic or not based on its structure. So what we could use here, for example, is a so-called random walk kernel. So what a random walk kernel is doing, it computes matching walks in the graph G and in the graph G prime. And the more walks it finds between the graphs, the higher the similarity between the two graphs is. So we try to find walks through this graph, and if we find similar walks, then we can increase the similarity counter. So that's called random walk kernel, and this then can be used to directly do predictions based on the structure of molecules, and that's very convenient, of course. And you might imagine that there are a lot of different kernels, so there exists a lot of different kernels that allow us to compare structured data and to do predictions directly on the structured data. And this, together with the kernel trick, this makes the support vector machine so powerful and one of the most used machine learning methods in the world. So to summarize this, support vector machines can be used for classification. However, which I haven't talked about, there is also an extension that's called support vector regression, so it can be also used for regression problems, but we haven't talked about this in this lecture. There is something that's called the hard margin SVM, so that's a supervised learning method that only works on fully linearly separable problems, which usually do not exist in reality. And then we introduced the so-called soft margin SVM or CSVM. So here in the soft margin SVM, we have this additional parameter C, which is a trade-off between maximizing the margin and minimizing the training error. And this then can be extended with the so-called kernel trick, which allows us the usage of kernel functions, so of similarity functions, to find solutions for nonlinear separable problems in an implicit higher dimensional space. So what should you know from this lecture? You should know what is a decision function and what is an hyperplane. What is the difference between the hard margin SVM and the soft margin SVM? And what different types of kernels do exist? Why do I need a kernel? Why are kernels useful? And you should know some of the basic kernels like the polynomial kernel or the RBF kernel, because these are one of the most used kernels, and these are the kernels that you might find in all of the scientific literature. So in computational biology, in biotechnology, and also in other domains, the RBF kernel and the linear kernels are some of the kernels that are very often used. So that brings me to the end. In the hands-on, we will show you how we can use scikit-learn and a support vector machine to do classification. So thanks a lot and see you in the hands-on.